This is a car moving, and we have a pendulum. So actually, I have here x1, y1, and x2, y2. Probably this is theta. How many degrees of freedom do we have? How many degrees of freedom?
Same.
2.
No, 2.
How much? How many degrees of freedom?
2.
2, right?
1 and 2.
2 for this guy, but it doesn't move vertically, so I removed one. And 2 for this guy, but I have a pendulum-like constraint, so I removed another one. So I have only 2 degrees of freedom. You have complete freedom to select what cues to start with and to live your entire problem with. For here, it's very convenient to talk about the x motion of the car, right? And probably theta for the pendulum. Okay, so these are my cues. I'm gonna write everything in terms of these cues. Actually, we were doing that in Newtonian mechanics. We have this freedom to select whatever we like. But like I said, the only difference that over here in analytical mechanics, I will generate at the end just 2 equations of motion directly. Whereas in Newtonian mechanics, you will have to generate 4 equations of motion and just play with them to get the really useful tool. Okay, any question about this concept of generalized coordinates?
Yes, sir. In this thing, we only have the liberty to make q1 equals to theta, q1 equals to x, but there has to be x and the theta. Only the relationship may vary.
Say it again, please.
You say that it's our choice that we can take whatsoever cues we want to select. The only option here is I have is that q1 should be equals to x1 or q2 equals to x1. That's it. Nothing else.
You have your options, yeah.
What other option do I have?
I mean, you can have your Q1 equals X2, right? So the thing is, okay, this is a good question. The thing is, whatever Qs, and this applies here and applies to Newtonian mechanics as well. Whatever Qs you're gonna select, you need to be able to write down the position vector of each mass, in terms of these variables only. You need to back out all the physical x's and y's of each mass in terms of these variables. Over here, if I know x, y, and theta, of course, I will be able to back up all the x's and y's for each mass. In particular, this is the x's and y's for the first mass. The x and y for the second mass, I can get them if I have x, y for the first mass and theta, for sure, right? The same here. If I know x1 and theta, I can get x, y's for all the masses. Simply y for the mass 1 is 0. And this guy, if I know theta and I know x, I can get the other x.
So this has to be sensible. Right? This has to relate.
The thing is, the generalized coordinates are the set of variables that you select. Okay? But you have to be able to write down the x's and y's of each mass in terms of these variables only. You have to be sufficient to completely determine the motion at each time. Okay?
So in this case, you could choose x2
Yes.
and
Yeah.
instead
X1.
of x1.
Yeah.
And,
I can choose x2 and y2.
y1 wouldn't make any sense. Like if we take y1 equals to some q's, it will be a loss.
Yeah, because y1 is simply 0, right? Two masses. So I have here x1, y1, x2, y2, and I have an angle theta. How many degrees of freedom?
One.
Yeah, anybody doesn't see that it's 1? 1. So what's the best degree of freedom to choose? The best Q?
y2.
That's not
Or
easy.
theta.
Okay. So Q, it's up to you, but it is good, right?
We could have done y1 or y2. Sorry, x1 or y1 or x2.
Yes. I don't see a bunch of erasers. Wow. Let me get this one. So this leads to the next concept, which is the configuration space. So in Newtonian mechanics, we have each mass, each particle move in a physical space, x, y, z, okay? Over here, we don't see the x, y, z anymore. We just see the q's. So it's very appealing to produce a space comprised of these q's. q1, q2, q3, q4, and so on and so forth. Okay, we call this space simply the configuration space, the space comprised of the configuration coordinates. So your system, Newtonian mechanics starts this problem. You have a point mass, starts at some point in the space, and just evolves under its own dynamics. Okay? Here, to me, the whole system, remember this is a fictitious space, because in this example, this is x, y, and theta. There is no physical space that comprises x, y, and theta, right? So this is a fictitious space. So my system will start with some initial condition, q1 initial, q2 initial, q3 initial. This may represent this point right here. And as the system evolves, each of these q's will evolve, and the system will have some trajectory in that space. So actually, this is an analogy between analytical mechanics and Newtonian mechanics. In Newtonian mechanics, this is a real particle moving in a real space. Over here, this is not a real particle. It's the initial condition of your system in this space. And this is not a real trajectory. It's the trajectory in the Q space, okay? In the configuration space. Any question about that? Any question? Yes, Anshul?
So your trajectory is independent of what you choose for Q1, Q2, and Q3?
What do you mean independent?
So that trajectory is essentially based on what you define for the Q's, correct?
Yeah, in the Q space.
In the
Yes.
Q space. So it does, that trajectory is essentially the same for any set of
You mean the
Q's?
exact shape?
Yeah.
No.
No, it'll change based on your Q.
Yeah, sure.
Okay.
So what do you mean by this? It's only an initial condition which is traveling in this space.
So your whole system, it may be a flapping wing microwave vehicle which has 20 degrees of freedom. I don't care. So this would be 20-dimensional space. To me, in analytical mechanics, I will only see it as simply a point mass evolving in that 20-dimensional space. Okay? Yes, Jeff?
So it has to be a subspace too, like a physical representation of the subspace. You can't have any Q1, Q2, Q3 possible
Oh yeah,
for your
yeah.
system.
But okay, and this is why sometimes it's called configuration manifold. Okay, so it is subspace of your physical space. That's correct. Manifold is just a curvy surface. We're going to talk about that in detail towards the end. Okay, what else? So this is 1, 2, 3. The work function. We have mass 1, subject to force F1 in Newtonian mechanics, mass 2, subject to force F2, and so and so. So the work function is the integral. Each mass dotted, maybe you have summation here, I1 up to n. This large n is the number of masses. So in all our notation, now n is the number of masses. Okay? Number of bodies. particles and rigid bodies. Dotted with the displacement of each guy, right? This is the work function. Like I said, we will work with scalar quantities, one of which is the kinetic energy. This is easy to get, 1/2 mv squared for each mass, and add them up. The other basic quantity in analytical mechanics is another scalar quantity. It's the work function. Here is its definition in terms of Newtonian mechanics. So it's each mass times, or